about to begin our final session. To start with, we will have two keynote speakers. Our first keynote speaker is Pablo Castro from GoogleAI. Pablo obtained his PhD from McGill University, specializing in reinforcement learning and sequential decision-making under uncertainty. After doing a postdoc in Paris applying machine learning techniques to taxi routing services, Pablo joined Google as a software engineer, building machine learning models for ads. After a brief stint in Chrome, building backends for machine learning systems, Pablo joined Google Brain, where he is currently a staff research software engineer, focusing on fundamental reinforcement learning and machine learning for creativity. And in his spare time, Pablo leads a jazz trio. Please welcome Pablo.
Hi, everybody. Thank you for having me. It's a real pleasure to be here and to see all the enthusiasm and all the amazing research that is happening here. And it's really incredible to see how much AI is becoming such a common language amongst not just researchers and people in industry, but everywhere. On the Uber ride here, the taxi driver was listening to some radio station where they tell silly jokes. It's just three dudes telling silly jokes to each other. And they had a long discussion about AI and the future of AI. It was still silly, but the fact that they're talking about it in such a non-technical radio station just shows how much this field is permeating society. So my name is Pablo. I'm based in Montreal in the Google Brain office there. And I have to turn this on. There. So just briefly a little bit of myself. I'm originally from Ecuador. I moved to Montreal to do my undergrad, worked for a little bit, then went back, did grad school with doing a pre-cup, did a little postdoc in Paris, and then I joined Google. You already heard all of this. So I've been with Brain for the last 2 years, and my research is mostly reinforcement learning and machine learning for creativity. And it's this last one that I'm going to talk to you about today. So just briefly, some of my other research. I'm the main engineer behind Dopamine, which is this framework that we use for reinforcement learning research. It's mostly for value-based research and discrete domains, if that means anything to you. But it's been quite popular. People seem to like it quite a lot, so I encourage you to check it out if you're into reinforcement learning. I also work a lot on trying to understand, both from a theoretical and an empirical sense, why distributional reinforcement learning tends to work better than expectational reinforcement learning. And this is, of course, with Mark Belmar, who's the guy that introduced distributional reinforcement learning. I work very closely with him. And then I also work on designing these metrics that allow you to define a distance between two states in a Markov decision process, where the distance is behavioral distance rather than physical distance. And so, like, lots of math, cool videos. So I'm not going to talk about this stuff. If you want to hear more about this stuff, you can come talk to me later. And finally, one minor plug. So I'm also involved with the XNA Coalition, and we organize these workshops in the main machine learning conferences. So we started with NeurIPS last year, and it was a tremendous success. We have a bunch of sponsors, and so if your paper gets accepted, if you're an oral, you'll get everything paid, which means you get flight, hotel, food, and conference registration. If you're a poster, I think we cover like half of it. But it's a really, really excellent event, and you get to be there with all the biggest minds of machine learning. So I encourage you to apply. The deadline is September 13th, so you still have time. All right, so now let's get into the talk. So I'm going to talk to you about machine learning and creativity, which is what I spend 50% of my time on. So many of you probably know that there's a lot of structure in music. So it can be from the harmonic relationships between the frequencies of the overtones of the sounds we hear, to the circle of fifths that many of us learn when we're studying music theory, to the the form of blues, the 12-bar blues that we listen to, the sonata form that composers use typically in the first movement of symphonies, and something even more esoteric like the 12-tone system of Schoenberg. So composers use these structures to write the music that we enjoy, and we implicitly use these structures to enjoy that music because it gives us a common language of understanding. So it's not just random notes where they're following some structure that we're used to and varying those rules a little bit so that it gives us some excitement. And so structure plays a huge role in music. One of the most well-known structures or set of rules that music students study all over the world is the theory of counterpoint. And so this is a set of rules for writing multiple voices that are independent but harmonically related. So probably the most well-known user of counterpoint is Johann Sebastian Bach. And so he could take a melody like the one I'm about to play here, And that's our test for sound. So let's try that again. Yeah, okay, just a second. Let's try that again. Nothing? I swear this was working earlier today. All right, let's try with the speakers, so I don't slow this thing down. No, sí, está. Sí, a lo mejor así. So, okay, we're going to have to use the speakers, and maybe we'll get another microphone because this thing isn't working. So, I tested it twice, and it worked. I swear. Anyway, you heard that melody. I'll play it again so you can hear it. Let's see. Let's test. Can everybody hear that? Could everybody hear the feedback? So hopefully there won't be feedback. All right, so Bach can take a melody like that and then use the rules of counterpoint to harmonize that, that single melody into 4 voices that are harmonically related, but each voice is independent, and write something like this, for instance. So that's very nice. Counterpoint took centuries to develop. It took about 9 centuries to develop. Finally culminated with this book in around the 13th century. And this was done through trial and error. Composers and musicians would write stuff, play it in churches, and then see people's faces, and that was their feedback. And then they adapted and did this for centuries. So they were essentially going through a bunch of data and trying to find the patterns in that data to try to figure out what works and what doesn't. And so going through a bunch of data and trying to find patterns is exactly what deep learning is good at. And that's what we do at Magenta, which is one of a team I'm part of. It's a part of Google Brain. And so we live at the intersection of machine learning, art, music, creativity. And so everything we do is open source. We release all our models. We release tools. We interact with Ableton. So there's some Ableton plugins you can have. There's blogs. So I encourage you to check it out. The link is here. I'm going to talk a little bit about some of the projects we do at Magenta. There's a ton. So if you're interested, you should check it out. Okay, today I'm going to talk about a few models that make use of this architecture, the transformer architecture that was introduced in this paper by some colleagues. So the transformer architecture is something for doing sequence-to-sequence prediction. So you can think of it like doing translation from an English sentence on the, can I do a pointer thing? No. An English sentence on the left to a German sentence on the right. And so the power of the transformer is that previously these types of sequence-to-sequence models would operate using something like a recurrent neural network or an LSTM, where you're maintaining sort of a summary of the history in a hidden variable. The problem with this is that it would tend to forget important things that happened further on in the past. So the key of the transformer model is the encoder. I won't go too much into detail. I prefer drawings. So the idea is that you have a sentence that you want to translate, and so each sentence has some representation. And you're going to update each of these representations by looking at the representations of all the other words or tokens around that. And you continue updating these representations until you get something in the end which becomes your final representation. And when you're decoding, you're going word by word. And each word, you're updating the representation by using both the representations of the input sequence and the representation of the previous words before you. So what's neat about this is that now it doesn't have to summarize everything in the history in a single hidden variable, but it can actually look directly into the past. And so when we look at some of the weights that we get when we're using these trained models, if we're translating, for instance, these 2 sentences in English on the top to the sentences in French, you can see that the semantics of it depends on what the last word is, right? So if the last word is tired, then it is referring to the animal. If the last word is wide, then it is referring to the street. And if you look at the weights in between some layers in the network that was used to train this, you can see that when the last word is tired, it is actually paying more attention to the word animal, and similarly in the other case. So this allows it to have some long-term coherency that wasn't really possible with things like LSTMs and RNNs. And so some of my colleagues varied this transformer architecture a little bit using something what's called relative attention. And they took a data set of virtuoso piano players playing on what's called a disclavier. So it's a regular grand piano, but it also has a way to capture all the performance digitally. And so we have this really nice data set that's open source for capture with these virtuoso piano players, and we trained it on this relative transformer model, or they did. And so I'm going to play you one sample from this model. So when I mean unconditional generation, that means we just basically told the model, make something up. And this is one of the examples of what it produced. And you're going to see a little red bar moving from the left over there all the way to the right. That red bar represents what the model is producing at that moment, and you'll see some colored lines going backwards, and that represents the attention. So what previous part in the melody that the model is paying attention to at the moment. You can see there's certain motifs that keep coming back, and this long-term coherence is really what gives these models the power to produce stuff like this. And then it stops. The reason it stops like that is because we have to train it on these 20-second snippets, because otherwise it becomes too heavy for the model. So the model doesn't know how to end a piece yet, but it's something we're working on. But this quality of music generation is something that just wasn't possible before, something like the transformer architecture. All right, so that's really cool. We can make these nice melodies and show them in talks. But what I'm really interested in, I'm a musician myself, and I'm really interested in how we can incorporate these ideas in performance, in live performance or in composition. So basically make them a part of the creative process and not just showcase what the model can do. And so for the rest of the talk, I'm going to show some examples of how we can do this. So one of my projects that I'm involved with is making a model that can help you write lyrics. And the way I approach this is I took a data set that I found on Kaggle of the top 40 hits of the last 6 decades, and I trained it using one of these transformer models as well, and then I produced something we called RIIAA. So I partnered with this Canadian artist, David Usher. He's very well known in Canada, especially amongst women above the age of 50. But he had a rock band in the 90s. He's a really cool guy. And so what we did is we took one of his songs, Sparkle and Shine, and rewrote the lyrics using this tool. And so these are some examples of the lyrics that we produced. The things in bold are sort of the starter line that I gave the model, and everything after is what the model produced. And so he didn't use the starter line, he used everything the model produced and kind of played around with it. So these outputs are very cherry-picked. The model was not very good. We had to put a lot of work into actually making it work and fit into the model. But it was really a success in terms of an artist and a researcher collaboration, because we actually made a song out of this, and we put it out and we weren't ashamed of it. So that was quite cool. But I was still kind of disappointed with the model because it did take a lot of manual effort, and so I wanted to improve on it. So for example, I would feed into the model this first line here, I'm your big and brave and handsome Romeo, and this is the type of output that the model would produce, just the same line over and over and over again. And that's not terribly surprising if you think of the fact that I'm training on pop lyrics, and pop lyrics repeat a lot. And the other thing we found is that spelling wasn't great, because sometimes spelling in pop lyrics isn't, or the way they write them online isn't great. And the themes that they used weren't also varied. It tended to be love and parties and things. So this is a problem with the data set that we're using. And so I called this the pure lyrics model. So I thought, all right, what if we take a different data set, a data set of fiction books? Surely that'll produce more interesting things, because fiction books are more varied, more interesting language. And so we had something like this, where yes, the language is more varied, but it doesn't really look like a song lyric. It just looks like a sentence with new lines thrown in randomly, and so like a sentence chopped up. So on the one hand, we have a nice lyrical structure that we have here, but it's kind of boring. And here we have something more interesting, but it doesn't look like a song. So why not do both? And so this is a paper that we have up on arXiv with my collaborator Maria. And the idea of it is we're going to train 2 transformer models. Originally, the transformer, what I do is when I was training with lyrics, is I take one line and ask the model to predict what the next line will be. So I can feed in all these pop songs and get something like that. So what I do now with this model is I decompose these words into their structure. And what I mean by their structure is something that looks like this. So what we have here is the number of syllables in the input string, the number of syllables in the output string, and then the parts of speech, so things like noun, verb, determinant, adverb, that type of thing. And then finally, we append this, the last phoneme syllable, so this is gold, just so that the model can rhyme. Okay, so this is what I call the structure transformer, and then I'm going to train this on the lyrics data set, but the lyrics decomposed into this structure. And then I'm also going to train a vocabulary transformer. And this I'm going to train on the data set of books. So originally, the way I trained it is if I took, for instance, the first lines of Old Man and the Sea, I would split each sentence in half and ask the model to predict from the first half the second half, and then from the second half predict the first half of the next sentence, etc. And so this is what we use for that pure books model that I showed. So now I'm going to do something different. What I'm going to do is I'm going to take the first half as is, using English words, and the second half I'm going to include it as part of the input, but in this structured form. So we only have the number of syllables and the parts of speech. And then the output of the model is going to be the second half that we included here, but materialized with English words, right? So basically what this is trying to do is that the first half is giving the model the context, the semantic context using English words. The second half is giving it the structure, so how many syllables, what the parts of speech are for the sentence, and then the model is trying to fill in those blanks with actual English words. And so the way the whole pipeline works is if I have one line, like this is my first line, the first thing I'm going to do is convert it into its structure, and then I send that to the structure transformer. The structure transformer will give me the structure for the second line. I'm going to concatenate that with my first line, send that over to the vocabulary transformer, and then this will give me my next line. Okay? So then we tried this out, and it seemed to work quite well. So if you compare, if we have the pure lyrics here, you can see it's doing what we expect it to do. It just sort of repeats the same thing over and over again. Pure books, it's kind of doesn't really look like a song lyric. It's just sort of sentences chopped up. And with our model, we have something that seems a lot more almost poetic and more varied than what we have here. So we do have some interesting rhymes like stranger danger and pocket delicate. The reason it says ABBA over there is because our system, you can specify what rhyming scheme you want. And so the model will try to satisfy that rhyming scheme, in this case ABBA. One thing we do find is that it tends to rhyme a word with itself, because a word always rhymes with itself. And so that's something we're working on right now. So because we're building this model to be used in a creative fashion, it's kind of hard to evaluate it numerically. Like something like blue score doesn't really make sense for this. But we did run some numerical measurements. So for instance, how many words are repeated, how many lines are repeated. And so in general, we see that we repeat much less than something like the pure lyrics. And we repeat as about on par with books, which is kind of nice. One thing that's interesting is we seem to use more unique words even than books, which is something that was quite surprising. And so it isn't surprising that that we rhyme more, because we're the only model that's actually trying to do the rhyming compared with the baselines. So this is quite encouraging, but it's still work that we have ongoing. We're working right now on trying to make this tool public so that all of you can write the next top 40 hit. And so it should be hopefully coming out in the next few months. Okay, so that's cool. I was able to train a model to use for writing lyrics. That's something we're going to use with artists. But what if you can't train a model, or you don't want to? It takes so long, it takes a lot of effort. Can we use off-the-shelf models in a creative fashion? One way to do this is to make delightfully silly things with models that already exist. So I don't know if you remember this harmonization that I played for you before. I won't play it again, but that wasn't actually written by Bach. The first line was, but the harmonization wasn't done by Bach. That was done by a model that was in this paper by some colleagues of mine. The same Anna is the same first author of the music transformer paper, so she's really, really great. And this model is actually the one that was behind the Bach doodle that many of you probably saw, which was super fun. And so this is what I mean by making delightfully silly things. They took a model that already existed, and a bunch of front-end people got excited by it, and they built this whole thing. We were able to collect millions of melodies that people wrote. That data set is now public and available for anybody. And it got people interested in music. It got people interested in machine learning. And it's just a fantastic example of how you can take something and make it accessible to people, make it creative, make it a tool for people to be creative, even if they're not musically trained using these machine learning techniques. Okay, and so another way to use kind of off-the-shelf models is to adapt the model's output of the distribution of a model's output to satisfy your personal taste. So for instance, this is work with some colleagues of mine in Montreal and Jesse Engel, who's a Magenta in Mountain View. And so the idea is here, let's say you have some generative model and it produces a distribution of things. So this is the distribution. And let's say this generative model produces killer guitar solos. So that's really cool. But now let's say a user comes along and says, okay, I like your model. It's nice, but I actually don't like all of these guitar solos. I only like a subset of them. I only really like jazz. So I only want this model to produce jazz guitar solos. So one thing you could do is retrain the model only with jazz guitarists. But that, again, takes a lot of time. You might not have the resources. What we're proposing doing in this paper is instead having the model generate pairs of outputs. So Pat Metheny and Eric Clapton, and then ask the user, which one do you prefer? So for this example, the user would prefer Pat Metheny. And so what we're assuming is that the user has an underlying distribution over all of these potential outputs. And the way the user is making their choice is by what's called the Barker choice rule, which is this thing over here. So if we assume that the user has this underlying probability distribution, what we can do is simply try to estimate the underlying user probability distribution with an estimate Q using something like Kullback-Leibler divergence or something like that. And if we're able to do that, then we can use this distribution to only generate samples that the user will like. And so one thing that's key here is that we need to do this with a fixed budget, right? We can't be asking people questions constantly. We want to try to do it with as minimum questions as possible and adapt quickly. So the other thing I wanted to mention over here is there have been methods that have been produced to do similar things. They tend to do what's called score maximization, so just maximize some objective function. The problem with that is that it can sometimes have a tendency to do mode picking. So what I mean by mode picking is it might converge just to this little bump here, and then let's say this is just Pat Metheny, so then it will only produce Pat Metheny solos instead of also producing like Kurt Rosenwinkel or whatever. So by phrasing this as a density estimation problem, we're trying to cover more of the distribution rather than singling out a single mode. So one way of doing this is this paper from 2008 that's called Markov Chain Monte Carlo with people. What they do is they start with samples of their model, a bunch of points, and then they sample other points in the neighborhood, and they ask the user, which one do you prefer? And if the user prefers the new point, then they'll move the Markov chain to that new point. Otherwise, they stay in the same one. If you run this for a bunch of iterations, these Markov chains will converge to their stationary distribution. And then each of these points basically provides an estimate of the underlying user distribution. And then you can just do like maximum likelihood estimation to estimate Q. We're also proposing in the paper something we call density ratio-based approach, where instead of trying to estimate Q directly, we're trying to estimate this conditional probability. So given already the two samples, what's the probability that the user will select the first one? And we can learn this via this Kullback-Leibler objective, which we can show that it actually the global minimum for that is exactly the ratio that we want. So this is the ratio, remember, that the user is using to select their outputs. So because we don't know what the true underlying distribution of real users are, we came up with some synthetic experiments. The first one is binarized MNIST. So what this means is that we trained a VAE to generate the MNIST digits, and then our synthetic users were essentially users that wanted only one digit as opposed to all the 0 to 9 digits. And so on the left here, we have this top row is trying to adapt to a user who prefers zeros. And on the left, this is using the density ratio-based approach. And here's using Markov chain with people. And here on the bottom, it's for the digit 5. So you can see Markov chain seems to work quite better. And you can see over here that Markov chain gets much better results. Over here, we used the SketchRNN model, which is a VAE that is able to draw sketches of different objects. And this one we trained was able to generate sketches from 10 different categories. And the user then was trying to get the model to only generate categories from sketches from one category. So in the top, I think this is clock, and on the bottom, or sorry, camera, I think on the top, and camera at the bottom. And again, the ratio-based approach and MCMCP here. And again, MCMCP seems to do a bit better, but it's still not great. And you can see that the number of samples that the number of times we've actually asked users for or the synthetic user for their preference is 2 to the 20, which is gigantic. Like, we're never going to ask users that many samples. So this basically is demonstrating what a difficult problem doing, phrasing this as density estimation problem. And we're working on new methods to make it a bit more sample efficient to be able to reuse whatever samples we've already obtained. But this is an initial investigation into that work. And hopefully, ideally, the hope is that then eventually we can actually use this with generative musical models and have it adapt to user preferences. All right. So then finally, another way to use these off-the-shelf models creatively is to adapt the model outputs to adapt it to satisfy your use case. So this is work that I've been doing over the past year. And I took some really, old, for today's standards, models from Magenta. They're really simple. They're just RNNs. So the first one is a drums RNN, where if you feed in a drum beat, it'll produce another drum beat that's kind of similar. And so the way I use this is as follows. So I'm going to start with a bass line. So I play a bass line versus this one. And so I'm going to construct a drum beat on top of that one. I call it a deterministic drum beat because it's the same every time. Given the bass line. So the way it works is first I'm going to add a bass drum beat on the first, a bass drum hit on the first beat of every measure. So it'll sound like this. And then I'm going to add a snare hit to match each of the bass notes. And then finally I'm going to add a hi-hat every 8th note just so that it sounds more groovy. Okay, so that's my deterministic drum beat. So I can send this drum beat now to drums RNN, and drums RNN will produce some other drum beat. Sometimes it matches well with the bass line, sometimes it doesn't, but that's kind of cool because then it forces you to write a new bass line. So this example is cherry-picked. It obviously matches really well. Okay, so this is for generating drums, but I also use it for generating melodies or for improvisation, really. So here, again, I'm using another really old, simple melody RNN model. The way it works is you feed in a melody and it'll produce a new melody, usually in the same harmonic key and it's about the same note density. And so the way I use it is if I'm improvising and I'm playing notes, these notes are being stored in a buffer in my system. So let's say I played that melody. So once the buffer is full, that melody will get sent to the melody RNN model. The melody RNN model will produce some other random melody that will be typically in the same key, so that's good. But one thing I don't like about this model is that they have to quantize things, so it's very robotic. So I don't like the rhythm, and even if it wasn't quantized, the rhythm doesn't match the way I play, and I want this to sound more similar to the way I play, because otherwise I don't really like it. So what I do is I just get rid of the rhythmic information, and I only extract the notes from this melody, so G, F, B flat, A, G, C, E, D. And so, okay, this is ready. And while all this stuff is happening, I can continue improvising. And so then when my new melody comes in, my new improvisation comes in, what I'm going to do is create a hybrid of my improvisation with the notes that the melody RNN produced. So I'm going to get rid of the notes over there and stuff these notes in, but keep the same rhythm. So it'll look like this. So if you don't know music notation, you can just see the shapes look the same, but where the little balls are different. So that means I'm getting the notes from here. Okay, so I have a blog post on the Magenta site if you want to check this out. There's also a JavaScript web app if you want to play around with it. It's not as responsive as what I'm going to show you because you can't do multi-threading with TensorFlow.js, but it's still kind of fun to play with. And all right, so let's try to do a demo. Let's hope it works. So I have to do a few things first. And while I'm doing this, one question I get asked a lot is, why am I even doing this? I've been playing piano for like over 30 years, and I don't need this machine learning stuff to play. But the reason I do this, okay, just a second. The reason I'm doing this is because it's nice to have models that produce melodies out of the box, but I'm really interested in getting these models to sort of push expert musicians out of their comfort zones. And it forces them to be creative in different ways that they wouldn't have normally been. So as a performer, I've been playing live for many, many years, and it's really easy to sort of go into your comfort zone. You know your pocket, and you know that you're going to nail it in that pocket. And so it's really easy to just go there all the time. But when you have something that's hopefully pushing you out of that pocket into something a bit more interesting, then you're forced to be creative in new ways. And that's sort of the motivation behind this work. So let's try this out. All right. Okay, so first thing I'm going to do is I'm going to record a bass line. And now I'm going to create that deterministic drum beat that I showed. Okay, now I have that drum beat. I'm going to send it over to the drums RNN, and it's going to produce a new drum beat, and we'll see if it makes sense at all. Not really. So I'm going to record a new bass line to try to match it. Sorry. All right, that's good enough. I'm going to throw some chords in there so it sounds a bit more melodic. Okay, so now I have a backing groove, and I'm going to start the collaborative improvisation with the robot thing. So whenever you see my face here, that means it's me playing everything. So I'm playing both the rhythm and the melody. And when the robot comes out, that means I'm doing this hybrid improvisation. So that means that I'm controlling the rhythm, but the notes are coming from the machine learning model. So to show that, I'm just going to play the same note here over and over. And typically you just hear the same note over and over, but because the notes are being picked by the machine learning model, it's going to be different. Oh. All right, here it goes. Alright, so it's always nice to end a song with a drum solo, so I'm going to turn the temperature really high and then send it to drums RNN. That's nice drum solo. Thank you. So I think we still have time for a few questions, if anybody has any questions. If not, that's also okay. Yeah. So to repeat the question, in case everybody didn't hear, I think the question, correct me if I'm wrong, is could I combine something like GPT-2 to the outputs of that text generation with something like this rhythm thing? Yes. I don't exactly know the right way to do it. I'm mostly interested in like jazz improvisation. That's just because I play. Typically, you don't have lyrics during the solos. So lyric conditioned melody generation is something that a lot of people are thinking about. The tricky thing is getting the training data. So there's two approaches. If you find a data set that has like phonemes, so these are the syllables you can think of the words, mapped to notes, then maybe you can train something with that. But there's one that I saw that some people put out a paper in archive. I'm not exactly sure, they don't have a link to the data set yet, so I'm not exactly sure how it is. But another you can do is, if you don't have that data set, try to kind of play around with these outputs creatively, which is what I'm doing here, right? So the data set doesn't have any jazz solos, so I'm adapting it, like using my own rhythms. And again, I don't have an answer for that because I haven't really thought about it too much, but there are always creative ways of using these outputs, and that's what I find really interesting, like not just training a new model to do everything end to end, but actually using what's there in new creative ways.
I'm gonna abuse the microphone here. I was supposed to distribute it, but I have a question. So is there anyone, or have you thought of using other types of input for the like or not like of the person, that is not literally asking them, hey, like, do you like it or not, but more like physiological responses or video that shows how they react to music or something like that?
Yes, I've thought about that. So I have been chatting with a neuroscientist at McGill that he's really interested in music a lot, and so we've been thinking about what if we put an EEG on a person and measure arousal. So EEGs are pretty good proxies for arousal. The problem is you can be positively aroused and negatively aroused, and the EEG can't differentiate that. So if we're playing, there's a likelihood that we'll play you music you hate, and the model will just keep sending you that because it can detect you're aroused. But I mean, yeah, you can probably do something that's a combination of both. The nice thing about EEG is that it's a continuous signal rather than a binary signal. So it's something we're thinking about. We haven't really started looking into this yet, but it's something we have. Hopefully next year we can start working on that.
Okay, thanks.
Thanks for the talk. Really cool graphics. So my question is about creativity in machine learning. What are your, and I'm just like asking for your thoughts. Do you think machine learning is like a tool that makes humans be more creative, or do you think at some moment we're going to be able to make algorithms that are in some sense creative? And how would you say they are creative?
Yeah, so I've had this discussion with many people. Actually, yesterday over lunch we were having this chat with Marty. I don't think any model, any computer is creative at all. Like, it may produce nice sounding things, but I don't think that it's creative or it's art. And the reason I say this is because for me, art has to be purposeful. There has to be a purpose. There has to be a motive for why people do this. So if you go to a modern art gallery and you see a painting that's just a white canvas with the red dot, I can do that. Why is that good? But you didn't do that. And the artist has a motive. The artist went through all of art school to sort of know everything that comes with the baggage that comes with art history. And there's a lot of hidden meaning behind that painting. And most importantly, there's purpose in that painting. When you have a GAN that produces a nice picture, cool. Cool. I mean, for me, that's all you can say. But it's not, the model didn't have some cognitive purpose to produce that model. It was the programmer that said, okay, now make me a image, and make me another one. And it's really whoever curated the outputs of the GAN that's being creative, right? So these GANs can produce as many images as you want. When the person was making the tweet or making their blog post, they selected a few of them. And I think that's where the creativity comes in, or the appreciation of beauty or whatever. In terms of whether these tools can be used to enhance creativity in people or replace them, I hope the former. And I think a big part of it is what we work on. So I do not work on these things to try to eventually have something that I press a button and it makes me a song I like. I want to build these things so that they're new tools for me to be more creative. So one way I think about it is, if you think of the 60s and the 70s, if you wanted to record an album, you had to go into a professional recording studio, hire a recording engineer, because otherwise it wouldn't have sounded good. And to do that, that's expensive, so you typically needed a record label to back you up, or you needed rich parents, something like that. Nowadays, we have things like Pro Tools and Logic and Ableton, and you can record it in your basement and make super high-quality recordings. And so these tools have democratized the production of music. Yes, of course, you end up with a lot of crappy music, but there's also a lot of really good music by people that wouldn't have had the means to do that in the 60s. So I see these tools as kind of the next generation of these democratizing tools using machine learning, so they can be personalized and they can be smarter in the sense that they're not just kind of following static rules, but they're adapting to the patterns that they find in the data. So for me, it's important that we work towards that side of things rather than to press a button and have it produce everything that musicians are doing right now. And then finally, I'm a musician, so I love doing music. Why would I want to make something that does music for me? You had your...
Thank you very much. I'm also a musician. I'm fascinated by this topic and the prospects not only of how machines can help humans to be more creative, but also how AI can make us understand better how creativity works in humans. So my question is more about, since I've been looking the research in Google DeepMind, that they use biological constraints to constrain the amount of memory they have access. If there's something similar that constrains the memory or the resources for creating, so they don't have hyper memory by reading all these database and try to experiment what are the results of this biologically constrained creative agent.
Yeah, I think that's really interesting, and I'm a big fan of constraints. If you have an open canvas with all the tools available to you, it's hard to start because what do I pick? Do I pick pastels? Do I pick crayons? When you have constraints, then you're sort of forced to use whatever you have, and some of the questions that you ask yourself are already answered for you. And I see that the demo I showed you, I kind of see it in that way. It's hard to. I've actually played with that live with paying audience, and it went okay. But it was hard to do because I had people in the audience watching me, and so I had to try to make it sound good, and that was an effort for me. Whereas if I didn't use this thing, whatever, I know how to play music, so I can do it. But so the constraints, I find them really satisfying because they do push you to new creative directions. I haven't thought too much about encoding biological constraints into this work, but it's an interesting thought I'll have to consider.
Have you done tests with real singer records?
For the lyrics, you mean?
Oh, for the register of the voices.
Oh, so no, I haven't played with the human voice at all. So the lyrics was all with text, and to be honest, analog scares me a little bit, dealing with waveforms. I'm not too familiar with it. I've done a little bit of it, but not too much. So I've been sticking with MIDI, and that's why you have these little dinky keyboards. Because it's nice, because then a C is just a C. But if you have recording the audio, the C will record the C of the piano, and then that car alarm that was sounding, and so that'll be difficult to really say for certain that it's a C. And if you're developing improvisations based on that, if you want to be harmonically consistent, then it gets kind of difficult. So no. But maybe in the future. I am thinking there's a new idea I'm working on that is using raw audio, so I don't know if it'll work, but maybe next time I'll show it to you.
Okay.
Hi, thank you. I was wondering if musicians that you work with who do this full time, the example that you gave us earlier, with the Canadian artist, are they generally resistant? What is their attitude around working with AI?
David is super gung-ho about AI. He loves AI. He's a really neat guy. He has startups that he founded on just exploring the space of AI and creativity. Some of it is more smokes and mirrors than AI, but he's still really interested in this space. So he was super keen to work on this. But at the same time, he's very demanding. So when I sent him the first draft of the model, I mean, by draft, I mean sample outputs, he called me and he's like, this is crap. I can't work with this at all. And so I had to tweak the way we were sending the starter lines to the model. And just doing that, I didn't have to retrain anything. Just doing that, it produced things that were a lot better. So there is some trial and error with this. I like working with him because he's coming at it from a very different perspective. So for me, because I'm a researcher, I'm not super into lyrics at the moment. I do like writing lyrics, but right now I'm more into the music side of things. I'm a bit more forgiving than him, but he is sort of pushes me. I mean, he doesn't tell me like, oh, you should add an extra layer or anything like that, but just this model's not working. It's kind of crap, and I can't use it. So then, all right, back to the drawing board and try to figure out what it is. So he's really excited about it. Other musicians that I've talked to, I think it comes to the way you phrase it. So I'm always phrasing it as these are tools. These are not, I don't want this to produce a full song. I want it to help you write a song. And so when you phrase it that way, they're usually pretty receptive and interested in it. And especially if you, what I like to do is provide tools that makes it easy to do things, not running Python scripts like I'm doing here, but just from the web, because then they can use it.
Yes.
Hi. Have you considered using these tools on other aspects of music, just as sound shaping or sound synthesis?
Yeah, a little bit. So I have this tiny demo online somewhere where I'm taking, so I'm interested in using machine learning models, not just the generative models, but any machine learning model in creative ways. So I have one that's just doing line fitting, so it's just like a linear regression. And I'm using the loss of that of the training process to adapt the modulation of a frequency modulator. So if you have a sine wave, I have 6 sine waves, and when it starts off, it sounds very dissonant because they're all way off. And when it finally converges, it converges to an E major chord. And so that you can hear the training and the learning of the model. And that type of idea I'm exploring a little bit with analog synthesizers. So yeah, hopefully I'll have something next year. I think we're out of time because, so thank you everyone.
Okay.